Okay, so let's do a little bit of checking that this formula that we used actually works. So once again, I'm just looking at page 441. Basically, we're trying to solve the system x prime equals ax. We have a multiplicity 2 eigenvalue that is defective. We use this word defective to mean that the dimension of the eigenspace is less than the multiplicity, the algebraic multiplicity of the eigenvalue. So what are our assumptions? We are assuming that, first of all, V1 is an eigenvector corresponding to the eigenvalue lambda, so that's this. We are also assuming this, which I wrote here. And let me translate that, because if I multiply this out, this is like AV2 minus, of course, the identity matrix doesn't do anything when you multiply by it, so this is just lambda V2. So that equals V1. And then I can rearrange that if I want. Maybe that'll be helpful. And what are we checking? What does this claim? First of all, this claims that we have this solution, which this is not a surprise. This is what we checked before. This is just a standard eigenvalue and eigenvector solution to a linear system, just like we checked before. The new one is this one. So let's check that this is also a solution. So that's the one I'm going to check. V1t plus V2 e to the lambda t. All right, well, I'm checking that x prime equals ax, so let's do x prime and let's do ax and just verify that they're the same. To do the derivative of this, I would have to use the product rule. This vector inside the parentheses is not a constant vector, but I can do the product rule. So the derivative of what's in parentheses would just be V1, and then the derivative of this is lambda e to the lambda t. Okay, nice. So then what would a times x be? Let me go ahead and just distribute this all the way. I'm multiplying by a, and I'll multiply by this too. So I'm going to have an a v1 t e to the lambda t, and an a v2 e to the lambda t. And yeah, so I have these two things. I'm checking that they're equal. Maybe I should have simplified the first one a little bit. So let me go, okay, v1 e to the lambda t plus lambda v1 t e to the lambda t, and I'm running out of space here, plus lambda v2 e to the lambda t. And let's see here. I know, what do I know? I know that a v1 is the same as lambda v1. So this is the same as this. So if we check, so I verified that this is the same as this. Let me verify that the rest is the same as the rest of this, which would be these two terms. So I would check that a v2 e to the lambda t equals v1 e to the lambda t plus lambda v2 e to the lambda t. And actually, whoops, we're blurry. We're back. I can cancel an e to the lambda t off of everything. Maybe I should have done that a minute ago, but c'est la vie. This is just checking that a times v2 is v1 plus lambda v2, which we know because of this, right? If I move this v1 over, it would tell me that a times v2 equals v1 plus lambda v2, which is exactly what we're checking down here. So it works. And again, this is, I've said this a few times. I don't know who noticed this or what they were thinking when they noticed this, but it does work and you can check it. I don't know how they figured it out, but you can check that it works. Most likely that they figured it out by guessing a bunch of things and then observing that one of their guesses was actually working when they checked it. There's a lot of trial and error goes into these things. You should know that this section does cover higher defects, which can happen. For example, so in this class, we don't really do big matrices. Like the biggest matrix that I ever even asked you to think about is probably a 5 by 5 or so. And even a 5 by 5, we were probably just using Maple to deal with it. We weren't dealing with it by hand. But in real life, matrices can get really big. You can have a 100 by 100 matrix, and you might have an eigenvalue whose algebraic multiplicity is 50, and its geometric multiplicity is 3. So its defect is 47. So these things can happen, and this chapter of the book does cover, at least theoretically, what you do in that scenario. Like we have these generalized eigenvectors where you have this sequence of vectors, like this equation down here is the same one we were dealing with, but then you would also have like a minus lambda I times v3 equals v2, and then a minus lambda I times v4 equals v3, all the way up. And I'm not gonna go into any detail about that. I want you to be aware that this method exists, just in case in life you come across such an example. But this is the type of thing where if I make you like memorize what you do, it's just gonna be a nightmare. So I don't want you to memorize what to do in this situation. I just want you to be aware that this exists. So just so if you come across it, you can look it up. So then what should I do? And yeah, maybe, okay. I'll just say a word about this. There's an analogy between repeated roots and repeated eigenvalues, because if you remember these like these higher order differential equations where you have like you turn it into a polynomial, like you have like y triple prime and that turns into r cubed, and then you have y double prime and that turns into r squared, and then you try to find the roots of that polynomial. And we talked about what you do if you find repeated roots is, instead of if you have a root of r, or say like a root of a, and this is repeated twice, then you're going to have e to the at, and then you're also going to have t e to the at. What you do for the repeats is you take what you would normally have, which is e to the at, and you start multiplying that by t's. And if it's repeated again, you have a t squared e to the at. And if it's again, you have t cubed e to the at. This stuff that we're doing now is vaguely analogous to that, at least in the sense that I'm just kind of pointing at an example, and the details aren't important here. The point is, if you have this is an example where you have a defect of, I guess, 2 instead of 1. So instead of just having a t, you also have a t squared. And again, the details aren't important. I'm just pointing out that the higher the defect is, you get these higher powers of t. That's all I'm pointing out. Just to say that there's an analogy there between these two things. Repeated roots of the characteristic polynomial of a higher order differential equation and repeated eigenvalues of a system. That's the analogy. So let's do an example, which this is not going to be really like higher order stuff, or like higher defect stuff, I mean. This is going to be a 3x3 example. And I'm going to cheat a little bit because finding eigenvalues and eigenvectors for 3x3s can get a little bit painful. This is number 16 out of the homework. So it's just to solve this equation. So we have a particular 3x3 matrix, and I have already, yeah, so obviously I already wrote some stuff down here. What did I write down here? So because I'm going to cheat, I used Maple a little bit here. I put in that matrix, and then I used the command eigenvectors. So the command eigenvectors, which I'm showing you how to do Maple Assignment 2 if you've looked at Maple Assignment 2. What that command does is it spits out something like this. This is a vector consisting of the eigenvalues. What this means is that 1 is an eigenvalue 3 times. It's an eigenvalue of algebraic multiplicity 3. What the columns of this matrix are the eigenvectors. That's how Maple gives you the answer. Notice that we got one that really, I mean, I called it an eigenvector. I shouldn't call the 0 vector an eigenvector. The 0 vector is not considered an eigenvector of anything. What this is indicative of, the fact that Maple is telling us that, is that there is a defect. There is an eigenvalue of multiplicity 3, however, an eigenvalue of algebraic multiplicity 3. However, there are only 2 linearly independent eigenvectors. So the eigenspace is only dimension 2. So we see that we have a defect. So what are we going to do? I'm going to go back to this. And, you know, I was telling you last time that I wasn't a fan of the way the book wrote this, but now I see the wisdom in the book. I do think this equation is important. And it wasn't so important for the example that we did. There wasn't a problem with the way I did the last one. But in some cases, this first equation can be very useful, and we're going to see that. What the first equation is useful for is that you can basically let V2 be any solution to this equation and plug that value of V2 in here to get V1, which will automatically be an eigenvector. V1 will automatically be an eigenvector if you let V2 be a solution to this and then plug that solution in here to get V1. So that's how we're going to do this. So, right. I know my matrix A. I cheated with Maple to figure out lambda equals 1. So what should I do? I should do A minus 1 times I. Whoops, how long have we been blurry? So what I did is I put in my matrix B in Maple. That's A minus lambda times I. Because if you look, the matrix for B, all this is the matrix for A. I subtracted 1 down the diagonal. So that's B. And what I really want is A minus, A minus lambda I squared. So I want B squared. So I did B squared. Yeah, I'm really lazy with Maple. Because I didn't even want to multiply a 3 by 3 times a 3 by 3. So it turns out B squared is just the zero matrix. All right, so what's that tell us? So to summarize, this is the zero matrix. A minus lambda I, what was this matrix B, which was this one. So how do we do this? Once again, V2 is just a solution to this equation. This is a very silly system. Yeah, this is free. This is free. This is free. Everything is free. V2 could be any vector. Why don't I... And again, I'm not interested in finding every solution. I'm just interested in finding a solution. So, because I am not creative at all, let me go with this. Well, okay, I don't want any solution. I wouldn't want the zero vector, but anything that isn't the zero vector that's a solution is suitable for this. And I'm not creative, so I went with that. So let's use that for our V2. V1 is just A minus lambda I times whatever V2 is. So A minus lambda I was this one. Write this a little bit better. Come on, stop being blurry. There we go. So I get 0, negative 8, 8. Okay, so let's summarize what I found so far. I have two solutions that should be linearly independent to my system, and once again, they are these. So I've got V1 e to the lambda t, so that would be 0, negative 8, 8, e to the t. Oops, couldn't see that. The other solution is all kinds of problems. V1t plus V2 e to the lambda t. So that's V1t plus V2. So this times t plus V2. I don't know if there's really anything I can do about this focus thing. So, like, the camera just automatically does it. I can't seem to shut it off, and it's trying to just focus on my hand, or it's focusing on something else. So I don't think it's too bad. I've watched the videos, and I don't think it stays blurry for too long, but we'll just deal with it. Maybe I'll stop talking about it so much. We got these, but we're not done yet. We're not out of the woods yet. This is a 3x3 system, and we got 2 linearly independent solutions. We should have a third one. What are we going to do now? The third one should be, roughly speaking, colloquially speaking, like a normal one. This eigenvalue only had a defect of 1. So, right. So once again, this had an algebraic multiplicity of 3, and it only had a defect of 1, meaning that the dimension of the eigenspace was 2. So we have one eigenvector. Remember, V1 is an eigenvector. There should be another linearly independent eigenvector. We just have to find it, and then our third solution is going to be that eigenvector times e to the t. That's all it's going to be. So, paper, here we go. So, well, all we need, another eigenvector of A, linearly independent with V1, and this will be easy enough, especially because I cheated a little bit with Maple. Once again, according to Maple, we have these eigenvectors, and yeah, so Maple says that a basis for the eigenspace is, I'm just copying down what it said, -3 halves, 0, 1, -3 halves, 1, 0. That's what Maple told us, basically. And I just need any eigenvector that's linearly independent with V1, which was 0, -8, 8. And since we're talking about a small number of vectors here, it's easy to tell whether one vector is linearly independent with another vector. If there's only 2 vectors, the only way they can be linearly dependent is if one of them is a multiple of the other one. So actually neither of these up here is a multiple of this one, right? So I could really take either of these. Let's say take, well, there's no reason not to just pick the first one. Yeah, so let me put my answer together. So here were my 2 linearly independent solutions before, and I said that my third solution was just going to be to find another eigenvector of A, which now I have, and my third solution was going to be that times e to the t. kind of like this one is an eigenvector times e to the t. I just needed another eigenvector times e to the t. And so my general solution is just going to be, I slap a constant on each one. So my general solution is x equals, say, c1. And then I'll do the first one that I wrote, plus C2, and then this one, plus C3, and then we said it was going to be this vector times e to the t. So there we go. This is all doable. Of course, I did cheat a little bit with Maple, but I didn't cheat in any like essential way that I couldn't have done by hand. We can do 3x3s by hand. It's just a little bit painful, and I didn't want this example to get bogged down by me showing all the work for that. But it is doable, and that's what you do. And I want you to remember that there is like higher order stuff happening here. Like you can have defects of higher order. The truth is, because realistically, it's painful enough to deal with a 3x3 matrix that the biggest defect that you would ever see is a defect of 2. So I'm not really going to cover the high defect stuff, but you should know that it exists just in case you one day come across an example like that. Okay, so I'm going to upload this and then give you some homework.